Okay, so since start has been completed, we are ready to proceed with the HTSeq, which will count how many reads we have on the genomic features. So if I will open here, if I will click here HTSeq count, and I have to use input and some parameters, and these parameters actually are quite important now. So I tried some test runs here on a single star output, on a single mapped file, and I will tell you some insights, and then we will go on with the normal analysis. So the genomic annotation that we had was this GFF file. Now if I will open it, it's this file here, and this file is a bit problematic for us because for the exons that we are interested in, the features that it contains here on the last column are not consistent. So sometimes it contains transcript ID, you see that here, transcript ID equals to that, which means that this exon belongs to a transcript with this ID, but this is not the case always. So there are several exons, we can see that like that. I search for the word exon, and then I search for the lines that do not contain the word transcript ID, and there are several of them. So for example, this line contains exon, but here there is nothing like transcript ID. If I search for something else, even the name gene, there are some records that do not contain the gene. Now why this is important, I can explain you what HTSeq does in a second here. So let's see why HTSeq is a bit problematic on what it does and how we will do it properly. So this is the software, and what does it is the following. It has a read here, and here's a reference genome here. And this reference genome has features. So for example, an exon is a feature, a gene is a feature, exon is contained inside genes, and so on. So this is a feature, and then this feature contains some information. So this section contains some information, for example, a gene ID, which is this section belongs to a gene with some ID. For example, CEP3031, just an example here. So several exons will belong to this gene ID. For example, if we want to see that graphically, this is the gene CEP3031, and we have an exon here and another one exon here, and then we will have some reads mapped on this exon. For example, this read will be mapped here, this read will be mapped here. Notice here that this read maps partially to the exon and partially to the intron. This read will be mapped here, this read will be mapped here, and so on. So what we have to notice here, if this read will be mapped here, then it's okay because it maps to an exon. So this is tick. Now let me put one more read here. This is okay. So read number 1, 2, 3, 4, 5. For read number 1 is fine because it maps to a feature that is fine for us, this exon feature. Okay, but what it will count is that it will give a +1 for the gene. So it will say that CEP3031, it contains one read. Okay, let's go to read number 2. Read number 2 partially maps to the exon, and this still is fine, as we will see later on the options of HTSeq. So this exon belongs to this gene again, so this one will become 2. Contains 2 reads now. This 3 read belongs to another exon, but also this exon belongs to the same gene, so this is fine. We have now 3 reads, and this is fine again, 4 reads. But this read now does not belong to an exon. It belongs to the gene but not to an exon. So since we map things on the exons, this is discarded. So for this attribute, we will have the number 4 on that. So again, reads are mapped to features, but what we count from feature is some specific information, some specific attribute. So what we will do in HTSeq is that we will map reads to exon features, but then we will count the gene ID features. And this GFF file that we have used all the time is a bit problematic because the gene ID is not present, or transcript ID is not present in all exon information. Now for that I downloaded another file from NCBI. Let me find it to demonstrate it. It's not here. Yeah, it's here. Okay. Now this is the web page of Genome Assembly for the C elegans, and if you go here to download, you can select a GTF annotation feature. We had GFF before, you can select GTF now, and you can download it. Okay, now this file is this GTF here, and if I visualize it, I see that all the time it has this gene ID feature attribute. Indeed, there is no single line for exons, so I search all the lines that contain the word exon, and then I search all the lines that do not contain gene ID, and I found none, which means that all the lines that contain the word exon also contain the word gene ID. Okay, that's some good. And what I have done now is that I have uploaded this GTF file on Galaxy, just using this upload again. But my problems do not stop here. But before going to the next problem, let me explain you what I said here. Which features of HTSeq actually are responsible for this thing here. Okay, this union thing is actually corresponds to this thing here. That if a read even partially matches to a feature, so this read partially matches to this exon, then it will count. Another case will be that this one, we have two exons of the same gene, and this read is like that. So again, this read will count as a read that corresponds to the gene ID of these exons. So union means that even if a read matches partially to a feature, it will count. Okay, this is the union thing, and it's what we use usually. Now the second option here is more tricky. It asks for stranded or non-stranded information. The three options are yes, no, reverse. So stranded, the help here says that specify whether the data is from a strand-specific assay or strand-specific library. Be sure to choose the correct value. So it's quite strict. It's quite gives some emphasis here. Be sure to choose the correct value. Okay, now I'm not really sure what to do here. So we have to find out if the specific data that we use come from a strand-specific assay, and first of all to understand what strand-specific assay is. Okay, if I go to the paper, I read here that using RNA isolated from single worms as input, we synthesize DNA, constructed sequencing libraries, and then evaluate the quality of our libraries by comparing them to standard RNASEQ libraries that were made with 2.5 micrograms of total RNA using the TrueSeq stranded mRNA library preparation kit. Okay, from that I understand that the library is stranded. Stranded library means that that we have information from where we get every read. So what means that we have information from where we get every read? Now we have the DNA here. And a gene is located here, right? This is double-stranded cDNA. Okay. So we had RNA first, and we converted that to cDNA, and then it became double-stranded cDNA. All right, and this is what we are going to sequence. But since we have paired end, we might sequence this end from here and this end from here. Now, stranded library means that we know from which of the two strands we took each read. So stranded means that we know if this read was taken from the plus strand and this read from the minus strand, or vice versa. We know the strands from the cDNA, that the reads are obtained. Now, why this is important? If I suppose that I know the strand, I will tell the program, go to see if this read has been mapped here, then it will not find it. If, however, I know that the library is stranded and I will tell him, okay, go to see if the read is mapped here, then it will find it, because this is mapped here exactly. Okay, then you might ask why not to use unstranded libraries. Why to say that, okay, I don't have information and my library is unstranded. The reason is that we might have less false positives. So a false positive is if we'll say that this read is mapped here, but actually it's not mapped here, so it will be a mistake. Now, stranded libraries help us to have lower false positives, but in order to do that, we must know that the library is stranded in this specific way, that this forward read comes from this strand and the reverse read comes from the other strand. This is one case, and the other case is that the forward read comes from this strand and the reverse read comes from this strand. Okay, this is the stranded case. We have two stranded cases. One is like that and the other is like that, reverse of the first one. And the unstranded cases means that I don't have this information, so please check if this read belongs here or here, and do the same for the reverse read, check if it belongs here or here. This might generate a few more false positives. This might be more precise, but we must know which case we have. So the paper informs us that the library that we use is stranded. However, I can't find anywhere if it is stranded on the correct direction or the reverse direction. Now this is problematic because here I have to choose if it is stranded yes or reverse. Alright, so yeah, this is also some information from a web page. It writes here, for HTSeq, the HTSeq count manual indicates that for the minus stranded option, stranded equals no means that a read is considered overlapping with a feature, regardless of whether it is mapped to the same or the opposite strand as the feature. For stranded equal yes and single end reads, the read has to be mapped to the same strand as the feature. Okay, for paired end reads, the first read has to be on the same strand and the second read on the opposite strand. For stranded equals reverse, these rules are reversed. Okay, let's dig a little bit more into that to understand exactly what it means. For stranded equals yes and single end reads, the read has to be mapped to the same strand as the feature. Okay, I go here again on the GTF. Let's visualize it a bit better. And I have an exon here. Somewhere I must have some exons. This is an exon. And let's see if I have any information about the strand that it belongs to. So here I see some strand information. This is a plus strand, plus strand, plus strand, plus strand. So it means that this section and this section and this section and this section belongs to the plus strand, the forward strand, while these sections here belong to the minus strand. Now if a read matches here on this section, then the forward read, the reads that are in the 1.fastq file should match the attribute on this direction, and the reverse read must match the attribute in the reverse direction. or vice versa if here I choose stranded reverse. If I choose stranded no, then the orientation here does not really matter. Okay, the problem is that if it is stranded and I choose the wrong information, so it's reverse stranded and I choose yes, then I will have many reads that do not match anywhere, because what the program will do is that it will try to match a read to this exon in this direction, in the plus direction, but actually it matches the reverse direction, so it will not manage to match it. Perhaps I should draw that. Okay, let's suppose that this is an exon A, C, G, T, A, and I have a read, and this is a plus strand, and I have a read that is A, C, G, T, A. Okay, let's put some more spaces here. Now clearly this read, this is a read, this is the reference genome, clearly this matches here. So what I should choose here is stranded equals yes. Okay, if I choose stranded equals yes, it will be fine. If I will choose stranded equals yes, no, it will be fine, because it will try to match this here and to the reverse complement. So T, G, C, A, T, 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 G, C, G, C, C, and it will match in the plus strand, so it will be fine. If I will choose stranded reverse, then it will just try to match this here and it will fail. So then this read will be considered to be unmapped. It will not. It will be mapped, but it will not count as a feature. It will not count as a read that belongs to this feature. Okay. If on the other hand the read that I have here is T, G, C, A, T, 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 then clearly this matches here, but if it is stranded equals yes, it will only try to see if it matches here and will fail. Okay, so we must be really careful what to put as stranded, so plus or minus. Now I did some experimentation, and when I put stranded yes, I really got very few results, very few reads, so this was clearly wrong. And when I put stranded equals reverse, then things became good. So what we will try here is I will specify that I have a collection of reads. I have all these reads that I want to map. I have this GTF file, not GFF, GTF file, it's this one, because it contains the gene ID information, union, reverse, and everything else is the default, and I just click on the run tool. Okay, things are there, and we have to wait. Okay, things go on here. So since I put a collection, I can see on the progress bar here that some reads some HTSeq runs have been completed and some others are going on. Let me click here. Okay, now these are the 6 forward reads that I put. Probably I must put all of them. And let's see what's going on here. So this is the no feature output, and from the 500,000 that I had, you see that only 1,762 has been matched to something that's called no feature, so to no exons in principle. Some of them are ambiguous, some of them are not aligned, but in total we are good. And the same is true probably for the other data sets. Now let's see something here. Okay, I just wanted to check here from the report of star of HTSeq. It writes that HTSeq count on collection here, HTSeq count, let's see, where is it? Yeah, I click here on a specific run of HTSeq, so it writes that the input file is RNA star on data 79 and 78. Okay, let's go to see what these data are, just to be sure that everything is correct. Okay, so I go back to history, 79 and 78. 79. It's the GTF. Okay, what's happening here? Okay, so yeah, it writes that HTSeq was run on this data, 178 RNA star on data 79 and 78. So this is the reference genome, the GFF file, and the mapped. I just want to see what the mapped are here. So I click on this to make it larger, and then some info here. So I will go now to the run of star. And then the forward reads were the trimmed files from 90 and 89. Let's go to check this. 90 and 89. Okay, it's not here. Where is it? Okay. The dataset specifically, for some reason I cannot see them here, but if I click on that and I click the details of star, I can see that star ran with both forward and reverse. This is what I'm going to check actually, that I have the forward and reverse mapping here. So everything seems to be fine. Again, I have just a few reads without good mapping, and everything seems to be fine. So if I go to main history, I have the bad reads, the ones that mapped somewhere in the genome that is not a good feature for us, is not an exon or something, and I have the results here, and I can just visualize them. I will click on that. I can click here, and can wait for a while. So it means that this gene here has 8 counts, this gene here has no counts, and so on and so forth. Definitely we will have some genes with several counts. Don't forget that we use only 500,000 reads. I can download this file, I'll save it here, and I can just show it better on the terminal. Okay, this is a result. So less says Galaxy 216. Okay, this is the information. You see that this one has 14 counts, 24 counts, and so on. I can sort it based on the number of counts, and there are some reads that have 9,000 reads, some genes that have 9,000 reads, and so on. Okay, so now I have my results done. It was a bit tricky with HTSeq. I just remind you what you have to do. First of all, when you use HTSeq, the usual thing is to check the mode union, so to allow for partial overlap between a read and a feature. Then for the stranded, which is the tricky part, you should know what if the library is stranded or unstranded. If it is stranded, then you should know the direction. And then you should use a proper GTF or GFF file. So the GFF that we had was not proper because it didn't contain consistent information for each exon. Sometimes transcript ID, sometimes something else, sometimes nothing. So I chose the GTF file, which contained all the time the gene ID information, and the results were good. Okay, the next thing will be to perform differential expression analysis, and we will see that later on.